So, work done by a spring. So, let's say we have, this would have been the equilibrium position, so let's call that x equals 0. Here is a wall, and we've got the spring and our mass. Right, so the spring here is in equilibrium, so here the force is equals to 0. Now we, by some mechanism, we manage to extend the spring. So this now becomes some sort of initial position, and obviously it will be from there to there, so that will be x initial. So obviously the spring tries to pull this mass back. So if this mass is now free to move and the only force on it is the spring force, it will start to accelerate towards equilibrium. So this mass will move. Over here, the spring force will be 0, but this mass will have lots of velocity. So it will move past equilibrium, and the spring will start to decelerate it. So the moment the mass moves beyond equilibrium, so somewhere over there, it's still got some velocity in that direction, but the spring force is acting in this direction. So let's say that's x final. Right, so we've got initially the spring is accelerating this object, so it's adding velocity, adding energy. Once this object is past equilibrium, the spring now says, hold on, I'm trying to stop this object. So then the spring starts to remove energy, starts to impede the motion of the object. Now we know that the spring force has to be equals to negative a constant times the position of this object. So if we draw this on an axis, so let's say that's the force by the spring, its magnitude, this is x. When we've got that x is positive, so if that corresponds to x equals 0, x initial is somewhere over there, and we've got a spring force in the negative x direction. So we will have some sort of negative value for the spring force. We know this is a linear equation in x, and let's say we've got x final is somewhere over there. So x final is a negative position, it's towards negative x, but the spring force now is positive. So it will be something like this. So that's the spring force at the final position. And we know the force changes linearly with position. So if I want to draw the force as a function of x, it gives me this line. So this is the force as a function of x. And I said that if you want to calculate now how much work does the spring do? So, well, we know this is equals to the area under the graph. So it has to be equals to this area. Sorry, not that area, that area. So it's this area and that area. So somehow the magnitudes of these areas tells me what the work done will be. So this area is equals to, so let's call this A1, let's call that A2. So area A1 has got a magnitude of whatever the force was at the initial position times the base. It's a triangle, so that has to be x initial itself, times a half. Right, and we know this will be, if we're just interested in magnitudes, we know f is just equals to negative k times x. So the magnitude of this will just be k times xi. So for now, I'm just interested in how large that area is. So I'm not interested in signs just yet. So that's the magnitude of the force times that. So we get a half k x initial squared. Similarly, the area A2, so that area over there, is equals to a half times the magnitude of the force over there times the magnitude of x final. This is again a half times k x final times x final squared. So if we now want to figure out how much work is being done, we said that if object is accelerating, so if the force is accelerating the object, it's doing a positive amount of work. If the force is decelerating an object, it's doing a negative amount of work. So this will be positive work because it increases the velocity. This has to be negative work because it decreases. It's the work done by the spring force to decrease the velocity. This means the total amount of work is equals to a half kxi squared. So the positive amount of work done minus the negative amount of work done. Okay, so no fancy calculus, just areas under a graph and a bit of physical reasoning, and you get an expression for the total amount of work done by a force in moving this object.